slide set. I hope it is visible. So we are discussing about this candidate elimination algorithms for computing the set of consistent hypotheses given a training examples. And we have seen that we are, in this case, we keep two bounds in the version space. One bound is on the most specialized set of hypotheses, and the other one is the or maximal set of hypotheses, and the issue. And the other one is the maximal generalization hypothesis. So these two we are computing, whereas the specializations bounded, it is updated every time we encounter a positive training example, and for the generalization boundary, we update it when you encounter a negative training examples. So in this case, this algorithm, its convergence is guaranteed if first we have considered now there is no error in the training sample, but the second one is also very important, that there has to be a target function in the form of the hypothesis also. That means there is an hypothesis which will be described this target function C. So which means the corresponding constraints, whatever you have imposed in formulating a hypothesis, those, by satisfying those constraints, there should exist a target function. If it does not exist, then you will get a null hypothesis space, which means it is not able to represent this target. Now, when actually these two boundaries coalesce, then you get a single, or a, that means both generalization and specializations, they become same. So you get a single edge or a set of edges, which are in fact both most specialized or most general. I think we should get a single edge in that case. So this is what we have considered. I mean, this is just I mentioned. Now, a few issues today we would like to discuss about this algorithm once again. And on top of that, we would like to also discuss some of the general issues in learning with this example, because this concept learning is a very good example which reflect various issues of learning that we will also discuss today. So first thing is that when you are using this particular algorithm, candidate elimination algorithm, as you see that every training example is narrowing down your version space. So for the positive examples, you are moving towards more generalization cases. And for the negative examples, you are moving towards more specialization cases. So in this way, the size of the version space is getting narrowed. But the question is that what is the order of these training examples? Is it independent? First thing, the final result is independent of the order. But while computing, the computational complexity or the number of operations that you require, does it depend upon the order of the training examples? Now, ideally, as you understand, since you are narrowing down, ideally, if you can get some order by which at every training examples, you are reducing the version space to its half. Maximally, you are reducing the maximally, not half, maximally the number of hypotheses in version space. If you can do that, then no, your convergence would be faster. So that is what I mean. Precisely 50% hypothesis. If you can prune every training example, that is a kind of best training example you can say. But it cannot be always done. Some example could be that say just an example how it affects. Say with this version space, suppose this is the stage of your version space currently, whatever you have seen. Set of training examples. Based on that, you have come up with this version space for by making it consistent with that set of hypotheses or set of instance training examples. Now you have an additional training example in this order, and which is shown here. Sunny, warm, normal, weak, warm, same, but its level, depending upon a positive and negative, you understand that the result will vary. So if it is positive, so it, as I mentioned, it generalizes the set S, that boundary, that maximal specialization boundary. And if it is negative, it specializes the G. So you can see that no, since weak is considered, so actually your generalization S will be generalized to, there will be three, like in this case, say this needs to be, for positive sample, this needs to be modified, right? This should be question mark. And then no, you have to see that whether all the samples are also accepting this. But once it is accepted here, and then accordingly, no, you have to find out in this case that no, whether this is also accepted. I think this is fine. This should be the case. If it is negative, that means if it is negative, then you can see that both this are to be changed, right? Because at this place, you have this, it is accepting this sample. So you need to modify this boundary G and also take the minimal specialization of that case, so that then G gets modified, and accordingly the other. So these you are not computing this. You are only computing S and G. So you need not bother about this, because once S and G are fixed, then others will be derived from them. So this will also change, but you are not computing them. So simply you are updating S and G only. So you need to generalize it, which means since it is rejected, so weak, so this should be, so the strong should come here. No, not which one? Yeah, because no, either it could be positive or negative. There should
Hello.
Yes.
Good morning.
Any question?
Mm.
I'm not getting you, Mamsi. Do you want to ask anything?
Mm. Mm.
No, please mute yourself. I'm not able to get any questions from you.
Sir,
Yes.
so I have a question. Like, if the example like sunny, warm, normal, weak, warm, same is negative, so we can choose either of the last four to be negative, right? So,
Pardon? You are saying that suppose it is negative.
yes. So
Then
we will
how do
specialize
you
G,
modify
right?
it? Then how do you modify it? That is your question?
Yes. So we can change normal to anything else or weak to anything else. We can change the last four parameters, right?
Yeah. See, you have to put it, since it is negative, you cannot put question mark here. You have to put strong here.
Hello.
And you have to put strong here.
Yes, sir. I am saying that why are we only considering the one factor weak? Why can't we consider the other ones also?
No, no. You see, you are considering not one factor weak. You are considering the whole tuple itself. But no, depending upon the kind of training examples you have, so you will find that it has its effect. No, that's why I have highlighted it. I'm not considering only weak. We are considering the whole record itself.
Okay, sir. That means if we change another thing, we will have to also change S, right? Because it is not more general than it.
Yeah. So you have to consider to change that G, right? The general boundary, because it's a negative sample. It is.
Yes,
It
sir.
is.
Got it.
Otherwise, it is going to be accepted here.
Sir,
Okay.
if this is a negative sample, can you just tell me what would happen with the S hypothesis?
Yeah. I mean, you check the algorithm. It also checks there also. But no, it update is mostly G, because in ACE, what happens? You assume already whatever positive samples are there, they are only positive, and all other are negative. So ACE does not look at the negative samples. So you don't need to check that. Only thing is that you have to check whether that specialization, it is a specialization of the of the hypothesis what you are giving in G. So that is the constant you have to check there.
Sir, in this example, suppose the S1 instead of strong there was a weak. So and this is a negative example. So just with disregard S, like it would be empty again.
No, I mean you have to find out. See, if you are saying that no, um, if there is weak and then if there is negative, then you have to consider what about the other. So you should check also these question marks. I mean other question marks also. I mean there you may find some hypothesis which will satisfy that specialized case. Only the positive sum. If it is negative, you are saying.
Yes, sir. If this is the
If
same example you are
no, no.
giving for
See,
the
if
negative
it
one,
is negative, then you don't bother. No, it is already rejected by this, by the hypothesis in S.
in the S, I'm changing the strong one to the weak one.
So, which means there was some hypothesis which was positive at weak, right?
Yeah, yeah,
So,
yeah.
suppose it was here uh, instead of strong, you are saying if it is weak.
Weak. And
Naturally, so you should disregard all these things, because of that only no others will be also there will be some effect. Let us not bother about that. Suppose this is weak and you get this is as a negative sample, right?
yes, sir.
But in that case, no, in that case, if it is weak and you have also got worms same as the specialization case, I mean all these things, so there would be a contradiction in that case because you are accepting it. So you should not have come at this stage. If you have come at this stage, which means there is a contradiction. You are right. If you get that, that will be a contradiction. Okay, so which means that your hypothesis will not be able to, you will not be able to represent your hypothesis into this particular space. So in ACE, we do not check any negative example. That is the conditions. You assume all other negative. So if you have derived at this condition, if you have come up at this condition, so there is a kind of contradiction in your sample, which means your hypothesis space is not will not be able to no not be able to handle. So that hypothesis will be basically negated once you modify G. Once you modify G, you will see that no, this does not become a specialized case of G, and you have to eliminate that. So you can see the algorithm. You have to also update S based on the update of G.
Okay, sir.
Okay, so this is the I mean, this is what we observe, that order of examples it matters for the intermediate sizes of SNG, but the final SNG will remain same, whatever may be the order. If you consider the whole training example set, whatever is your training example set, once you complete uh, the uh, the full, all the elements in the algorithm, once you visit all the elements and update SNG, so final result will be the same. Now, there is another interesting aspect when you are using this version space. We can consider when you are classifying any new instance, we can use all instances of this hypothesis which are in the version space to find out what is the strength of your decision, which means that no, if it is satisfied for all such instance, all such hypothesis in your version space, we can say it's a very your decision is a very reliable. Whether when you find that it is partial, then you can give certain weightage. So let me. So you can use some voting procedures. Voting is basically if you find suppose here there are 1, 2, 3, 4, 5, 6. Say there are 6 such hypotheses which are there in the version space, and you know that they are consistent with respect to our training examples, right? Which means they all satisfy that conditions that whatever samples in the training examples are accepted, these hypotheses they accept them, and whatever samples they reject in the training examples, they all these hypotheses they reject them. That is the consistency part. Now you have a new instance. Say this is the new instance: sunny, warm, normal, strong, cool, change. So can you tell me that no, how many hypotheses will satisfy, or whether any hypothesis will satisfy?
All the hypotheses.
All hypotheses satisfied.
Right. How do you say so? Is there any, because you said all, did you check all the hypotheses one by one?
So the most specific
Yeah,
hypothesis
most specific,
satisfies.
if it is accepted by most specific, you can extend that, because that is the property of generalizations. So since it is accepted by the hypothesis in S, which means it should be accepted by all other more general hypotheses in that version space. Okay, so that is the first way of checking, instead of checking everything. Suppose this one you get: rainy, cool, normal, weak, warm, same.
Not satisfied by.
Rejected by the general hypothesis.
It is rejected by the general hypothesis, so it will be rejected by all other hypotheses in that version space. Is it clear? Okay. Yes. So which means that these decisions are very strong decisions. Huh? They are. Take this one: sunny, warm, normal, weak, warm, same.
Three will be satisfied.
Pardon?
3 will be satisfied.
Which are the hypotheses? Can you just tell me?
Satisfied by general but rejected by specific.
Rejected by S, it's satisfied by G, and also there is another hypothesis where it should be satisfied. Huh?
Yes, the middle line, second one.
Middle one. No? Middle one. Yeah. So that means 3 out of 6. Okay. This one: sunny, cold, normal, strong, warm, same.
By the general one and the first and the second.
General, and then that means sunny all question mark, and sunny question mark, strong all question mark. I hope. No. Yeah, that's right. These 2 only, which means 2 out of 6. So this is what I mean. If you get the version space given any instance, you can also check that how strong is your decision in the process. Right. So let us again try to understand that incompleteness of so incompleteness. I just referred to it, that it may happen that your target concept is not representable by the hypothesis, the constraint you put on the representation of hypothesis. That means the target concept does not exist in your hypothesis space. So this is what no, the assumption, and then only those algorithms will give you a result. Otherwise, no, you will get an empty space, though target concept may be there. So one example has been, we will understand with one example. Suppose you have a target concept like sky equals sunny or sky equals cloudy. Now, you understand that no, this is difficult. I mean, this is not representable by the average. So we'll see that. So consider, so this is your target concept, and with respect to this target concept, suppose you get this level, and which are also consistent with respect to this target concept, right? You get, say, sunny, warm, normal, strong, cool change, you get Y. Yes. Cloudy, warm, normal, strong, cool change, you get Y. But rainy, warm, normal, strong, cool change, you get a negation, N. Right? So when you are applying this candidate elimination algorithm, you can see also that first two hypotheses, first two training examples if you use, then you will get a question mark, warm, normal, strong, cool change. That is the hypothesis. And then once you get the negations, now then actually version space becomes empty, because your in your generalization cases you cannot put rainy there. No, there has to be sunny with all question mark. And since you have this negation, I mean, then there is a contradiction between, and you have to remove the specialization case also, and your version space will be empty. So this is I just mentioned. I hope you have understood that. So that is what I was telling you, that if you consider the first two training examples in your candidate elimination algorithm, then you will get the most specialized boundary. The hypothesis in the most specialized boundary will look like this. You agree with me? S will look like this if I take the first two training examples only.
Yes, sir.
Yes, sir.
Yes,
And of
Yes,
course,
sir.
G is still having all question mark, isn't it? And then I have not written that, but that is understood. And then if you have this negation, then you will have all this problem. And your new hypothesis is overly general, because this is rejected by this is accepted by the hypothesis in S, but it should be rejected at this instance. And so there is no way you can now represent it, because that in that the form, the constant I already mentioned, only one literal can be there or all literals should be there in the hypothesis. So that is the problem, right? So our hypothesis space does not include this target concept, so you will not get this target concept. So the guarantee that you will get a hypothesis that it is representable through your, it is representable. So there is certain kind of assumptions that needs to be true over the training example sets or over the space. So you need more expressive hypothesis. Now, there are always a catch. When you are having more powerful representation, then you may land up with a situation that is not useful for your representation also. Suppose you represent each and every instance in your sample space in a table. You consider all of them and with this level. Now, that can be also considered as a hypothesis by that all literals are there by using and logic there itself in the conjunction form also, but that is not useful. It's a kind of lookup tables, but size of the lookup table will be huge, and search will also take a lot of time. So, and if you have a very large space, it is not practical. Anyway, so we consider those kind of learners are unbiased when actually you do not have any constraint on your hypothesis formation. So, for example, with respect to these Boolean constructs, you allow all Boolean operations, primary operations that and or not, you allow them, and then it does not have any bias to your hypothesis formation. But as I was mentioning, that it is not useful because your hypothesis space will be very large, and representation, so get that representation also may require a large space itself. Okay. So also in the version space, the kind of voting strategy you have used, that also becomes meaningless, because most of the cases you can see that 50% of them will agree and 50% of them will not agree if you have exhaustive representation of this space. So that's why these assumptions are very important when we are forming this hypothesis. I think there was a question in the very beginning, and very very relevant question asked by one of the students, that why we are not considering the full form of Boolean expressions. Why we are considering them? Because of these ones. So we would like to find out certain order in the process. Now, as you put these assumptions, we are trying to reflect upon those orders. That is the kind of thing. So theory and your understanding of the system and process, that only can introduce this kind of thing. So these are toy examples which may not be very clear from the from this point of view, but when you look at certain domain and you build up a model, there you see that the structure of the model, the form of the model is very important there. I mean, you cannot just take very arbitrarily any general representation of a model, mathematical representation of a model, then it may not be practical to compute with it. So, so you should have certain constraints on this, and those are called inductive bias, because it is by observations you are putting those constraints, by certain some from some other experiences you are putting these constraints. So this kind of thing. So you are putting certain limit. You are limiting your connectives to conjunctions. So in this case, what happens that it has more power in generalizing the the rules, generalizing the model. Right? So that is the advantage you have. So we'll have a little more formal definition of inductive bias. So you see that when we say how do you, represent an inductive bias, you can consider that if the bias means you are trying. You are defining those constraints on your arguments, on your logical system, that using those constraints you can derive the same result what otherwise a deductive system would have done. So a deductive system, so now it has become a deductive system. So if you add those constraints, rest of the things will be following this. Say for example, suppose you have data points, say in two-dimensional space, you have data points, and we would like to so given the value of x, you are predicting the value of y. So you would like to determine the value of y. Right? Now, if you put a constraint that the relationship would be, in this case, say it is like a straight line relationship, say y equal to x plus b. If you put that constraint, now if this is this is your inductive bias. So if you put that thing, and then if I give you two points, and if there is no error, naturally you can derive the straight line equation, and then it becomes given any point x you can compute that. So something like that. So unless you put that constraint or put that assumption that they are related by these straight line equations. So I'm not saying linear, because straight line is affine relationship. So you can say affine relationships. They have an affine relationships. So then you can represent them. So that is one example. Even candidate elimination algorithm, what we have worked on, we have considered those assumptions. So we'll come to those things. So what is this? That you are logically representing these systems by as I mentioned, that with your logical arguments, you can derive the same output. What otherwise you are observing through learning in your with your inductive bias. So this is the formal definition of the inductive bias. So you can see that for any learning algorithms, inductive bias is a minimal set of assertions. So it's because these constraints are put in the form of assertions, which could be a predicate, which could be a Boolean expressions for satisfying certain things, or certain statements like the target function should be in the hypothesis space. That is also an assertion. Or the form of the hypothesis would be like this. So that is also assumptions. So it's a minimal set of assertions B used to logically infer the value of target function for any instance from B is that set of assertions, D is a set of training examples, and uh, for any instance, that instance is X, right? So if you have the unbiased learner, which is rote learner, we say that means you enumerate every possible instance and also you note, record what is the output, what is the level of that instance. Now, that is a kind of rote learner. So you have enumerated it and then you have stored it and it is your model. So it's kinds of lookup table model. So once you get an instance, you just simply consult your model, your table, you get that answer. So there is no, actually there is no inductive bias in that case. You are not putting any other, it's a free representations. As I was mentioning that no, in many cases it is difficult to go by rote learners, but in some cases limited when you have your input space small inside, when it is manageable, you can use this kind of rote learners. So rote learners does not have any inductive bias. When you consider the version space candidate elimination algorithm, the algorithm which we discussed just previously, so there you see that the assumption is that the target concept C can be represented in the hypothesis space. And if I consider the first algorithm on hypothesis formation, find S, there I already mentioned these two assumptions. One is definitely the target concept should be in the hypothesis space, and all instances that are not positive or negative. So I mentioned it many a time. So you see that's an assumption here. So the other issue that we will be discussing with respect to that algorithm, that what is the computational complexity of version space? Now it depends upon that how many elements you need to compute for the version space. So when you are computing the elements of version space, so the size of the version space is important. Now you see that the size of the whole version space is not so important. Rather, the size of these two boundaries, that most general set of hypotheses and most specific set of hypotheses, S and G, those sizes are important. So if you can restrict those sizes in the polynomial order, then possibly there is a polynomial order algorithm. Otherwise, if the size itself is exponential, definitely the algorithm has to be exponential. So that is what we usually say, that it is linear, the size of S, but it is usual. It is not. It is sacrosanct. It could be exponential also, and size of G, many times it goes to exponential in the number of training examples. But in more expressive languages, both S and G can do it. So for the candidate elimination, it is linear. Sorry, for the candidate elimination, it is linear. So the order of processing examples, because no, you are in candidate elimination, you are simply observing the positive examples. No, that doesn't mean so that is its linearity is there. It's a find S algorithm, so that is how it is linear. Yeah, it is same as whatever the find S algorithm provides you. At least no, your candidate elimination will give that S. The additional task of checking whether it is specialization of the hypothesis in G, that will take time, but the size of S will remain same. The order of processing examples significantly affect computational complexity. So one example we can show that when S is S is of certain, here S is constant. Size of S is small, but size of G could be exponential of the number of inputs. Say you have one positive example, all true. So this positive example, now you have the attributes. So this is a dimension. Each attribute is a binary valued attributes. It has either true or false. Now it could be of any dimensions, say d dimensions, whatever. So now suppose you have n dimensional. There are n such attributes. So when you are, so always your most specific hypothesis would be all T, because that is the only positive example. So always it will be that. But when you are getting a negative example, every time you are modifying it. So your first initial no set of hypothesis in that will be all question mark. That is what is your initial point. So next iteration, when you are coming to this this example, which is a negative example, you can see that these two together cannot be false. So that's why these are the two possible no hypotheses, general hypothesis, which will satisfy this and also which will which will reject these conditions. You agree? So you get, in this case, you get two in numbers. So next, in the next iteration, what you will get, and when you see the next sample, now in this position, see, both these positions cannot be F. This is already included. So now you have to modify because of these positions. Now you say these two positions, the same thing. So with this, for each combinations, you will have again another two. For each you will have two. For this, you will have these two generalizations, and I mean generalization means specialization of this. You have two specializations, and for this you should have these two. And for if you have your negative examples in this pattern, if it follows this pattern, at every step you are doubling your size of your G. Right? You get so many number of hypotheses. So finally, as you understand that, you will get the sizes in this form. So your size of S will be 1, but size of G will be 2 to the power n by 2. So which means it's exponential in the order of the samples.
Sir?
Is there any question? Yeah.
Are we assuming that we are having two false in a negative example?
You are having?
Two false arguments or attributes in a negative example?
No, they are negative examples. Yeah, it is that structure is like that only. I mentioned. No? Only those two are false. Then it would be negative.
So what would happen if only one is false? So the size will remain the same, right?
It will be accepted. If only one is false, it will be accepted. See, these are the only negative examples. That needs to be rejected by everyone.
Okay, so got it.
Okay, so now I will switch over to the concepts of a bit more generic concepts of learning with respect to our discussions on this concept learning, and we'll see that how can you express the power of hypothesis, expression of hypothesis. We have discussed in some form, so we'll try to see in this way, and also we can also find out that what is the probability that you will get a hypothesis which will be representing the target concept. Because the idea here is that you see that where is the catch? Catch is here. You are observing only a subset of in your space. Though your training error is 0, which means whatever you are observing, those are all true levels. There is no error in your leveling, right? And based on that, you have formulated a hypothesis. You have derived a hypothesis. But there are many hypotheses, as you all have already seen that in your version space, there are so many other hypotheses which also represent the which also satisfy that. And suppose in your case, your target function is something which is I mean your target function is something, and sometimes it may happen that your target function does not exist also in the hypothesis space also. So suppose you have your target function which are true for all the training examples, but for any other instance, if you take any other instance in the space, there would be they may not agree. So they may be same or they may not agree. So there could be error. So we are talking about error. So our training error is 0, but we have test error. We call it test error. We will come to those terms later on. So basically, we have true error. We are calling it true error because no, your hypothesis is not exactly representing your target concept. It is partially satisfying with your training examples, and it may satisfy also on some other samples which are unseen, but there may be some samples where it is not satisfying. So that we need to understand. So then, no, we consider in that distribution of the instance space, in that population distribution, uh, there are, with respect to hypothesis, there is a probability that certain samples, certain outputs may not be the same as the output of the hypothesis. So we call it basically the error. That is the measure. It's the probability that your result is not your output of the hypothesis is not the true output. So based on this, we'd like to see that uh, what is the what is the catch? Catch is that as you go on observing training examples more and more, no, you are basically so. Am I you guys hear me?
No, sir.
So your voice is breaking.
Can you hear me? Now, yeah, I'm
Yes, sir.
sharing my presentation.
Yes, sir.
Is it visible now?
Yes,
Yes,
sir.
sir.
Please tell me. So this is a concept that uh, actually
Student, you may leave the class. There is an internet issue. So from tomorrow we'll continue from that part.